Namaskaram. Now we know the Fourier series of a function. In this session, we will develop two special type of Fourier series, that is called half-range Fourier cosine series and sine series. The solutions of last homework. We know that Fourier series of a function, periodic function f of x, with the period 12 is like this, and a naught, a and b n's are given by these formulas. And it is clear that our function f of x is defined in the interval of length 12. Okay, half-range cosine series means a series representation of a function f of x defined in the interval 0 to 12. Suppose this is the function in the interval 0 to 12. Then half-range cosine series means a series representation of this function in terms of cosine only. Okay, that is the concept of half-range cosine series. For developing such series, the first step is we have to extend this function in the interval minus L to plus L such that new function is even. And what is the meaning of even function in the interval minus L to plus L? Geometrically, an even function in the interval minus L to plus L means that function is symmetric about y-axis. Okay, it's like a reflection about y-axis. So geometrically, what is that? Geometrically, that even extension is like this. Okay, so the next question is, let it be f of x. Suppose our new function is f of x. This f of x is defined in the interval minus L to plus L, and now we know that this is even. Then my question, what is the analytic representation of this function? The first one is clear. This side is clear. When 0 less than x less than L, it is clear that the capital F of x is same as small f of x. Suppose minus L less than x less than 0. Suppose x is in between minus L and 0. Then what is the value of this f of x? That means suppose x is somewhere here. Then what is this height? That is the value of the function at this point. It is clear that this height is same as this height because of the symmetry. Okay. And what about this point? If this is x, then this point is minus x. Clear. Now x is in between minus L and 0. So x is negative. So minus x is positive. Then what about this height? This height is nothing. That is f of minus x. Okay. So value of the function at x, if x is negative, that is equal to f of minus x. So this is the definition. So f of minus x. So this is the definition of this function capital F of x in the interval minus L to plus L. It's clear that this function is even. Yes. So this is the even extension of the small f of x in the interval minus L to plus L. And we denote this entire function as capital F of x. And one important thing is this capital F of x and small f of x are same in this interval. Okay. Now this capital F of x is a function which is defined in the interval minus L to plus L. Yes, its length is 12. So now we are ready to find the Fourier series of this capital F of x. Now you can find the Fourier series of this capital F of x in this interval. Okay. So these are the formulas for evaluating the Fourier series of capital F of x in the interval minus L to plus L. The Fourier series is given by this formula, and a naught is given, an is given by this formula, and bn is given by this formula. Okay, but now we have one extra advantage. What is our extra advantage? Yes, now we know that this capital F of x is an even function. So what about a naught? Yes, this is of 1 by 12 and minus 8 minus L to plus L f of x. F of x is even, right? So that is 2 times integral 0 to L capital F of x dx. And what about this one? You can cancel these two. So this become 1 by L integral 0 to L over this interval. What is our capital F of x? Yes, in this interval, capital F of x is small f of x. So this is f of x dx. So this is our a naught. Similarly, what about an? An is 1 by L, and capital F of x is even, cos is even, so the product is even. Okay, so again you can use the same rule. So 2 by L integral 0 to L capital F of x cos n pi x by L. And similar to the previous case, in this interval you can replace this capital F of x by small f of x. Okay, so this becomes 2 by L 0 to L small f of x cos n pi x by L dx. And similarly, what about bn? Here capital F of x is odd function, sorry, even function. Sine is odd function, so product is an odd function. An odd function, integral from minus L to plus L. So Bn become yes 0. So these are the changes in this Fourier series. Okay, so this Fourier series representation is a series representation of capital F of x in this interval. So suppose I am going to restrict our Fourier series in the interval 0 less than x less than L. In this interval, this is the Fourier series of capital F of x, but we know that in this interval, capital F of x and small f of x are same. Right, in this interval, capital F of x and small f of x are same. So this is the Fourier series representation of, and this Fourier series is called half range cosine series of f of x in the interval 0 to L. Okay. And also one more thing, for expanding the Fourier series of f of x, we assume that this capital F of x is periodic in the interval minus L to plus L. That means you can extend this function using the periodicity of capital F of x. Okay, here the period is 2L. So you can extend this function like this. Okay, or similarly, you can extend this function on this side also. This is the idea. So combining all these things, we can define the half range cosine series. So this is the half range cosine series of f of x in the interval 0 to L. A naught plus sigma n equal 1 to infinity a n cos n pi x will pi L, where a naught is given by this formula and a n is given by this formula. There is no bn. There is no bn in this series because bn's are 0. Okay. And there are two cases in this Fourier series because this Fourier series is also developed from our normal Fourier series. Okay, so it satisfies all that conditions. That means if f of x is continuous, then the Fourier series and f of x are same. If f of x is discontinuous, then Fourier series is equal to average of the limits, as similar to our normal Fourier series. Okay, so this is the idea of half range Fourier cosine series. The advantage of cosine series is this series expansion involves only cosine terms. Okay. Okay, next we have to develop a Fourier sine series. That means a series of this f of x only involves sine terms. Okay, suppose a function is defined in the interval 0 to L, and similar to the previous case, here we are going to extend this function as an odd function in the interval minus L to plus L. And what is geometrically an odd function? Geometrically an odd function means it is symmetric about origin. So geometrically this become, okay, so this is the geometry of an odd extension. The entire function is an odd function. Okay, it is symmetric about origin. Then what is analytically, what about this function? Yes, if x is in between 0 and L, then we know that our function is same as small f of x. So it is no doubt small f of x. Suppose x is in between these two, minus L and 0. That means suppose x is somewhere here. Then how to find this length? This length is same as, first you consider the minus x. Minus x is somewhere here. And take the function value at minus x, that is this height. Then put a minus sign. Suppose this is 5. Then this one is minus 5, like that. Okay. So this is nothing minus f of minus x. So this is the definition, or this is the analytical definition of this odd extension. So odd extension is f of x is equal to minus f of minus x if x is in between minus L and 0, and f of x if x is in between 0 and L. Okay, next we are going to find the Fourier series of this capital F of x by assuming this f of x is a periodic function with the period 2L in the interval minus L to plus L. That means you can extend this function using the periodicity. Okay, suppose in the interval L to 2L, the function is like this. Okay, and similarly in the interval 2L to like that, you can extend this function. Anyway, now we assume that this function is periodic with the period 2L. Then we know that the Fourier series of such function is given by this formula, the same formula. Okay, so what are the changes in a naught, an and bn because this capital F of x is odd? Yes, here f of x is an odd function, so it is clear that this integral is 0. And similarly here capital F of x is an odd function, is an even function, the product is an odd function, so this integral is also 0. And in the case of bn, this is an odd function, this is also an odd function, so product is an even function. So this become 2 by L integral 0 to L capital F of x sin n pi x by L dx. And we know that in this interval capital F of x is same as small f of x. Okay, so in the case of odd extension, the Fourier series involves only bns, non-zero bns. A0 and ans are 0. That means this series expansion in terms of sign. Okay, that is called Fourier half range Fourier sine series. And one more thing, actually this expansion valid in this entire region. We are concentrating only the region 0 less than x less than n. Okay, in this region our capital F of x is same as small f of x. So in this region we have a series expansion in terms of sign that is called half range sine series. Yes, so formally we can define the half range sine series of f of x in the interval 0 to L is like this. S of x is equal to sigma bn sin n pi x by L, where bn's are given by this formula. Okay, and similar to the previous cases, we have two cases. If f of x is continuous, then Fourier series and f of x are same. If there is a discontinuity, then we know all the discontinuities are jump discontinuity. Then the value of s of x is equal to average of the limits. Okay. So two important things in half range series is, one is function is defined only in the interval 0 to L. The next one is half range series involves any one of the trigonometric terms, either sine terms or cos terms. And these half range series are useful when we dealing with the heat problems and wave problems. Okay. Anyway, we will solve the problems related to this half range series in next session. Okay. Thank you.